This is one of a series of lectures produced by the Further Mathematics Support Programme for A-Level Mathematics Revision. In this lecture we're looking at the Edexcel Decision Mathematics 2 specification, and the topic is network flows. The specification says that you should understand an algorithm for finding a maximum flow through a network, the idea of cuts and their capacity. You should be able to use the max flow min cut theorem to verify that a flow is a maximum flow, and you should also be able to consider multiple sources and sinks. Note that vertex restrictions are not required, and also you will only have networks where an upper capacity is to be considered. You won't have minimum capacities. So if you're looking at other boards' questions or textbooks, then do be aware that they sometimes will include these other considerations that you do not need for Edexcel. Well, the basic idea is then that we have a network of arcs starting at some point S, known as the source, and coming in eventually to a point T, which is the sink. And what we have to do is to maximize the flow. So the flow capacities will be indicated on the arcs by some number. So for example, number 8 here would just simply show that the maximum flow through that one, let's say it went from S to A, was equal to 8 units. Now by flow it could literally be a flow of liquid, but it could also be costs, it could be number of pedestrians using pathways, all sorts of different things that could be asked in the context of network flows. The idea of a cut is that we can divide the set of points into two distinct different sets by literally taking a cut which goes through the network and divides the nodes into what's called the source set. That includes S, and the sink set, so the set of points which includes T. The cut capacity then looks at arcs which are going from the source set to the sink set. But if a line is going from the sink set to the source set, that one is not included in the cut capacity. So to calculate the cut capacity, you simply add together the capacities of those which are going from source to sink set, but not including those going from sink set to source set. And the cut capacity is simply the sum of those. If there are multiple sources, so for example if we had another source coming into A and perhaps going off somewhere else, let's call these S1 and S2, and likewise there might be multiple sinks, so T1, T2, possibly T3 even. The way to handle these is simply to use what's called a super source or a super sink, and we add in a source S or super source S, which has got arcs from it to S1 and S2, where the capacity of those arcs is sufficient to feed the arcs coming out of each of those. So if S1 had 3 and 4 as its capacities, then the arc from S to S1 would have to have at least 7 as its capacity. And likewise for the sinks, we would have each of these joined to a supersink T, where again the capacity was sufficient to take everything that was coming into T1, T2 and T3. So in other words, we're not having any restrictions anywhere. The way the algorithm works then, it starts off with any feasible flow through a network. That's often given to you in a question. And then from that start point, you try to see if you can improve the flow by using what are called flow augmenting paths. These are paths which start at S and end at T, along which as yet the capacity is not yet full. So we just simply need to go through the diagram looking for forward facing arrows, or arrows along which there is greater than 0 possibility of change. That will become clear as we go through some exam questions, which I will do now. This is a typical exam question. In particular, it's from the June 2010 paper, question 5. So reading through it then, it says that figure 2, which is shown, is a capacitor directed network. The number on each arc represents the capacity of the arc, and the numbers in the circles represent the initial flow. So we have to be sure that we know what's going on there. The 34 on SC, for example, is the capacity, and the 30 is the initial flow, so the flow that we're going to use initially in our solution. It says state the value of the initial flow in part A of the question, and then we need to work out the capacities of cuts C1 and C2, which are shown on the diagram, and then entering values along DH, FH, FI and IT. We need to complete the labeling procedure on diagram 1, which is something which is in the answer book. Using this completed diagram 1, increase the flow by a further 4 units, and you must list each flow augmenting route that we use. So we're told that we should be able to find routes which give us an increased flow of 4. And once we've done that, prove that the flow is now maximal. Well, the first part of the question asks for the value of the initial flow. We can get that either by looking at those arcs coming out of S, alternatively those coming in to T. So if we use those going into T, we can see that the flow is 31 plus 10, so giving us a total of 41. So for the capacities of the cuts, remember that we've got to look at arcs which are going from the source set to the sink set. So marking those on cut 1, we've got SA is in the correct direction, BD is in the correct direction, ED is EF, not GE, but CG. So those are the ones that we're going to be using, and from those therefore we get a total of 8 plus 15 plus 5 plus 11 plus 20, giving a total of 69. And of course you'll see that I've actually made a classic error there of writing down 2 of the flows rather than capacities. So the actual answer is correct at 59, but we should have written down capacities of 10 and of 25 to give the value 69. For cut 2, I've indicated the arcs which are going from S to T, ignoring the others, and those give a total of 64. So the cut capacity of C2 is 64. Moving on to the next part of the question, the diagram shows the initial flow pattern and the possible changes that can be made. We've been asked to look at 4 of the arcs which have not yet been completed. But just to explain what's going on, if we look at the arc from A to D, there is a flow of 6 and a capacity of 8 in that arc AD, and that's shown by the changes that can be made in that route from A to D. We could increase, in other words in the direction AD, we could increase by 2, or we could decrease by up to 6. So now looking at DH, there's currently a flow of 18, so the possible reduction is 18, but with a capacity of 24 we could possibly increase that flow by 6. At the moment FH, there's a flow of 13, so that's the possible reduction, and the possible increase up to its capacity of 15 is 2. If we look at FI, that has got currently a flow of 6. Therefore we could reduce by 6, but the pipe is actually saturated, or that arc is saturated at the moment. In other words, we can't actually increase the flow along FI at all. In I to T, we've got a current flow of 10, so that's the possible reduction, and we could increase by 5. We now move on to the idea of flow augmenting paths, and what we're looking for now is any path starting at S and finishing at T where the arrows going along the direction we wish to travel have got a number greater than 0. So for example, we could go from S to B, and then we could go from B to A, and then from S to D, D to H, and finally H to T. And if we look along there, the smallest number in that direction is 2. So S, B, A, D, H, T, we can increase by 2 units. Now to increase the flow, the backward facing arrows are going to go up in number, so that's going to go from 3 to 5 on SB, and the forward facing arrows will reduce, so from 2 down to 0. So always remember that the backward facing ones increase and the forward facing ones decrease by our 2. If we look at SD at the top, the backward facing one is going to increase to 8, the forward facing one reduce to 0. Likewise in DH, that's going to go to 20, not to 16, that's going to increase, and the forward facing one, I beg your pardon, reduces to 4. Finally, in HT, backward facing increases and the forward facing decreases. We now want another flow augmenting path if we can find one, and if we look at S, we can't go to B because that's already saturated, and we can't go to A, that's saturated. So we must start off by coming down from S to C. We can't go to E, so we'll go to G. Can't go to I from G, but we can go to E, and then from E to D, then to H, and then to T. So this path is going to be S, C, G, E, D, H, T, and it increases by 2 again. So performing that increase, then we get as follows. right up the top at DH. That one is going to reduce to 2, that one increase to 22, and finally 35 and 0. Again, a slight error in my arithmetic there, just checking through. That should have changed from 5 to 7, not to 8. You can always check through these because the total should remain the same. So it is always worth making sure that your totals at any stage haven't changed, which is what I just did as I walked through there. And it's now correct. Now we were told to increase by 4, which we've managed to do, and the question then says prove that this is a maximal flow. The best way to do this is to try and find a cut which has got a cut capacity which has got equal to the flow that we found. So at the moment we've got a flow of 45, so we're trying to find a cut with that as its capacity. So it's worth then looking at the paths which have been saturated, because the cut with the correct capacity would always go across saturated arcs. So if we just mark those in, just mark in the saturated routes that we've got on our diagram. These are all the ones where we've got 0 in terms of going forward. There's quite a lot of them are actually saturated on this particular diagram. I think one finally at the end as well. There are a few different cuts we could make. For example, if I mark this one in, you can see that having the saturated arcs helps. There's actually a simpler one, however, which comes in here. Either of those would do. So if we take the cut, the second one there, that's the cut HT, FI and GI. Now we need to write down the capacities of those. These are the capacities and not the flow, remember. Now the capacity of course is the back facing arrow here, so that's equal to 35, 6 and 4, and of course because these are saturated, then those capacities would also be equal to the flow in those pipes. And there we've got a total of 45. So we can say we found a cut of capacity equal to 45, but this is our flow, and therefore the flow we can say is a maximum. Well, that's the end of this lecture on network flows. Other modules and other topics from Decision Maths 2 can be found on www.furthermaths.org.uk.